Hey everyone, Law of Universal Gravitation problems are back, number 3. What is the distance from the Earth's center to a point outside the Earth where the gravitational acceleration due to the Earth is 1/12 its value at the Earth's surface? Okay, so I'm going to start off this problem with a picture to really help us visualize what's going on. Okay, so I'm going to draw a simple circle that's going to represent the Earth. I've got the radius of the Earth here. I'll call that r subscript e. Now, we know that the acceleration due to gravity at that point, GE, is 9.8 meters per second squared. Now, what we're doing is finding where the acceleration due to gravity is 1/12 this value. Okay, so we're looking for a larger distance because the acceleration due to gravity is getting smaller. We'll call that new distance Rn, n for new. So we're looking for that distance where the acceleration due to gravity, Gn, for a new acceleration, is 1/12 the acceleration at the Earth's surface, Ge. Okay, so Gn is 1/12 of Ge. This mathematical relationship is going to come in quite handy in a moment. Okay, now, the equation for the universal gravitation is Fg equals Gmm over r squared. Now, in the case of the Earth and an object, we can let the lowercase m be the Earth and the uppercase m be the object. It really doesn't matter which one you pick. Okay, so let's do this. Earth at the surface, we can make the following expression. By the way, currently I'm trying to come up with an expression for acceleration due to gravity, lowercase g. So at the surface of the Earth, we can say that the force of gravity, Fge, is g, mass of the Earth, mass of the object, over the distance from the center of the Earth to the surface squared, which happens to be the radius of the Earth. Now, we also know that if you want to just find a simple formula, right, for the force of gravity of an object on Earth, it's Fg equals mg, where this m is the mass of the object. Now, take a look at this. If we set these two equations equal to each other, like we did in video 88 yesterday, if you take a look at the similarities, you've got mass of the object, mass of the object. So g must therefore be represented with gme over re squared. Okay, so if you just take a look at that, there is quite a strong relationship right there. G must be equal to that expression. So we're going to say g is equal to, rather ge, the acceleration due to gravity on the Earth, is g times the mass of the Earth over radius of the Earth squared. Okay, so we're going to stay with that for a second. That's at the Earth's surface. That's how we find the acceleration due to gravity. That's where 9.8 comes from. Now, let's look at Earth at a further distance. Okay, so at a further distance, we're talking about Gn, Rn. Okay, so based on this formula, we can say that Gn is equal to Gme over Rn squared. See, Rn is the distance from the center of the Earth to that new location. And we also know that Gn is equal to 1/12 Ge. So I'm going to make that substitution for Gn there. I'm going to plug that in. Okay, so 1/12 Ge is equal to Gme over Rn squared. Now, Ge, there's Ge. I'm going to plug in this Ge over here and simplify. So here we go. 1/12 bracket Gme over Re squared, close bracket, equals Gme over Rn squared. So I hope you see that there's a lot of things that are going to cancel out now. We're going to cancel the g's, we're going to cancel the masses of the Earth, and we're left with the 1/12 Re squared on the bottom, Rn squared on the bottom. I want to simplify this into a nice expression with everything in the numerator, and luckily for me it is going to work out like that. I'm going to take the 12 Re squared, multiply it across to the numerator on the right, take the Rn squared, multiply it to the left, making it in the numerator on the left. So we're going to end up with the expression Rn squared is equal to 12 Re squared. At this point, we're trying to get Rn, so take the square root of both sides. Okay, so square root of Rn squared is Rn. Square root of 12 times Re is what you get on the right. Okay, so now plug in your values. Root 12, the radius of the Earth is 6.38 times 10 to the 6 meters. As I mentioned in video 88, if you don't have that number memorized, I would do it. After all, you are going to be doing enough problems that you'll inherently memorize it, but regardless, It lets you do problems a lot faster if you already know it. Okay, when you plug in those numbers, you're going to get 2.21 times 10 to the 8 meters. And because the question is asking us, what is the distance from the Earth's center to a point outside the Earth? Therefore, this Rn that we calculated from the Earth's center is correct. Some questions are going to say, what's the distance above the Earth's surface? If that's the case, take this number and subtract the Earth's radius, and you'll have it. But for the purposes of this question, we're good. So that's our final answer. Guys, be sure to click that like button if you like the video, and subscribe to Physics in the Flesh so you never miss a video from me. See you guys tomorrow at 12 noon with video number 90, Law of Universal Gravitation, Part 4.